Hello. So in this video, we're going to talk about Haberman's section 3.4, where the focus is on kind of differentiating Fourier series. Right. And so the main question is, right, if we have a Fourier series and we want to take the derivative of the function, kind of that gave us this Fourier series, are we allowed to just differentiate the terms of the series, right, term by term, and then end up with the Fourier series for the derivative of the function? Okay. So I'll make that precise here in a little bit, but that's kind of the focus for this section. So kind of the outline for this is set up the main problem, right? What do we mean by term differentiation? What are we hoping to get out of this? What is the motivation for all of this? We'll look at a specific example, which will show that kind of in general, cosine and sine series behave a little differently if you want to differentiate them. We'll look at each of cosine and sine series kind of separately and look at their properties under differentiation. And then finally, we'll talk about this thing that we're calling the method of eigenfunction expansion. But in practice, it's using Fourier series to solve PDEs. Okay, so what is term by term differentiation? And kind of why might we want to consider this? Right, so consider, right, heat equation, where we have a prescribed temperature at the two boundary points. That prescribed temperature is 0. And we also have some initial condition, initial temperature distribution. And so using, right, so this is via separation of variables. So using separation of variables, we constructed these solutions where, right, we have some constant times a spatial piece, which is a sine function, times these exponentials. Okay. So, right, so we were able to construct these solutions using separation of variables, but one question then is maybe so maybe one way of phrasing this question is, well, if we just plug in the series, so plug in the series to each of these pieces, does it still solve PDE? And I mean, it should, because we constructed it to. Right, but what if we distribute these derivatives, right, across all of these terms over that infinite summation? So if kind of this process is allowed, if we can differentiate term by term, right, so here we're taking the t derivative in u, and we're applying this t derivative to each of the terms. So back here, right, so we're taking here, say, d dt. In here, this doesn't depend on t, this doesn't depend on t, so the only thing that depends on t is this. And so we're applying d dt to here. And so what do we have? Well, derivative of an exponential is just that exponential. This constant is going to come down, and so we're going to pick up a minus n pi over L quantity squared k that's going to sit right in front there. Okay. So take the t derivative, right? We said this piece right here is going to come down, and that's exactly what's written here. Okay, so if we can differentiate term by term, this is the series that we end up with, right, for the time derivative of u. Likewise, if we take x derivatives, okay, so going back here, right, so looking at this is a constant. This doesn't depend on x, so the only thing here that depends on x is this. So if we can differentiate term by term and distribute that derivative, those derivatives will only hit this, right? So the derivative of sine n pi over L x is cosine, or n pi over L times cosine of n pi over L x. Take another derivative, then you're going to pick up a minus n pi over L. So you should end up with here a minus n pi over L quantity squared times sine of n pi over L x. And so that's exactly kind of this piece. This is the second derivative. Maybe I can write that explicitly. This together with this. This is the second derivative of sine of n pi over L x. Okay. And so the question is, okay, well, looking at these series, do they satisfy this, right? Well, if we multiply a k here and distribute it across all there, right, and then compare what we have here to here, we see that, well, with the k here, this series is exactly the same as this series, right? So if we can differentiate term by term, then, you know, it all works out. Kind of the series satisfy what we want. Okay. Okay, and so what's kind of the main question that we're interested in here, right? Well, let's see if we can generalize this. So focusing just on the spatial piece, right, that's kind of giving rise to the sine and cosine. The question is if we have a general Fourier series that takes this form, right, a linear combination of sine and cosine pieces. If we differentiate kind of the function, right, we're going to get the derivative of the function, sure. But then the question is, can we distribute the derivative across all of these terms? And so what does that look like? Well, distribute the derivative across all those terms. The only pieces that depend on x are the sine and cosine. So the derivative would affect those. And so then the derivative of this, we'd get a minus n pi over L sine. The derivative of this, we'd get a n pi over L cosine. Okay. And so then the question is, right, is this valid? Is this formula true? And kind of the answer that we'll see shortly is, well, sometimes. And so we'll talk a little more about, you know, what that entails. So one observation before kind of moving on and talking more about these Fourier series is that, right, so suppose you have, so right now, let's just focus on the cosine pieces. Right, so suppose you have a cosine series like this. Okay. Now, if you differentiate it, say term by term or otherwise, right, you're going to get something like, or you might get something like, the derivative is going to look like the sum of minus n pi over L, a n sine of n pi over L x, okay? But the observation is, right, so here, right, given this representation, our function f is even, right, just because we're working with cosine terms and each cosine term is even. And what we notice is, when we take this derivative, the resulting series should just have sine terms. And so then if this equivalence is valid, then the derivative of the function will be odd, right? So we started with an even function, took the derivative, ended up with an odd function. And so here the observation is coming through kind of these series, okay? But it turns out that in general, it's true that if you have an even function and you take its derivative, you're going to get an odd function, okay? And so that fact kind of motivates, right, why we would expect some of these formulas to hold. And so we can, I mean, make that more precise and actually kind of prove these things in a not bad way. So kind of there are two statements. One, if your function is even, then its derivative is odd. The second statement is that if your function is odd, then its derivative is even, okay? And the proofs aren't bad, right? They're just straight up computations, right? So here f is even, which recall means that f of minus x is equal to f of x. And we want to show that the derivative is odd, which means f of minus x is equal to minus f of x. Okay. Okay, so how we're going to go about it is, well, take the derivative of the function. Okay. Now what we're going to do is we're going to write it in a way so that kind of we're highlighting the fact that we're taking, right, the derivative of this entire function f of x. Okay. Now what we're going to do is we're going to say, well, f is even, so f of x is equal to f of minus x, right? Now here we're taking the derivative of the composition of our function with negative x. Okay? So then the chain rule comes into play, right? What is the chain rule? Well, derivative of the outer function times the derivative of the inner function. So the derivative of the outer function is just f prime, right? The derivative of f. But now we're evaluating at negative x, the inner function, times the derivative of the inner function, which in this case is just -1. Okay. So what we end up with is f prime of x, right? F prime of x is equal to minus f prime derivative at negative x. And so shuffling things around, you end up with this, right? So if the function that we started with was even, then its derivative is odd. You can do the same thing if you're starting with an odd function, right? So if your function is odd, right, same first steps here. But now, because your function is odd, right, so this you can rewrite as minus f of minus x is equal to f of x. And so this expression right here, that's what we've written right here. Okay. Now we have a constant, -1 in front. Derivatives don't care about constants, so we can pull this constant out. That's what's right there. Otherwise, again, it's the chain rule. So we're taking the derivative of the outer function, right? So f prime evaluated at -x times the derivative of the inside, which is -1. These signs cancel, and so we're left with f prime of x is equal to f prime of -x. And so in this case, the derivative is even. So these are just nice little general facts about even and odd functions. Yeah, okay. So going back here, right? So the main question for all of this is, right, when is it the case that if we take the derivative of the function and we differentiate the series term by term, the resulting series is the Fourier series of the derivative. Okay, and so claim is, well, it doesn't always hold, and so the so what we're going to do is actually show a counterexample to when, you know, the Fourier series of the derivative is not what you get by term differentiation. Okay, so what is this counterexample? Well, we're going to start with the Fourier sine series for x. Okay, so what does this look like? Well, right, how do we sketch Fourier series? It's going to be something like this. Okay. So I mean, you can think of it as, right, sketch x on this interval, take the odd extension to the entire interval, but x itself is odd, so it's no problem. And then otherwise, right, copy the profile over and then mark an x at all the points, or at all the points of discontinuity where, right, the value of the Fourier series at that point of discontinuity is going to be the average of the left and right limits. Okay, so this is the Fourier series that we're working with here. This is a sketch of that series. And so the question is, what do we get if we differentiate each side? So differentiating this side term by term, right, what do we get? So let me write it out. So the derivative of the nth term here is going to be, so copy over this constant over in pi. The derivative of sine n pi over Lx is going to be n pi over L cosine of n pi over Lx. So we get cancellation with the n pi's, we get cancellation with the L's. So the term by term derivative of this thing is going to be 2 times -1 to the n plus 1, all times cosine of n pi over Lx. And so that's what's written right here. Okay, so that's what we get by differentiating the series term by term. And notice that this is a cosine series. Okay, the derivative of x is just 1. Okay, so if term by term differentiation was valid in that, right, differentiate the left-hand side, we get the derivative of the function, differentiate the right-hand side, we get a Fourier series. Okay, and so when we say term by term differentiation is valid, means that, right, the series we get by differentiating is exactly the Fourier series for the function. So if we were allowed to do this process, if this process is valid, we would get that the Fourier cosine series for 1, which is the derivative of x, is this expression here. Okay. Right, but keep in mind that, right, for cosine series, constants are allowed. And so if you have a constant, right, well, what should the cosine series be? It should just be that constant, right? And this is definitely not constant, right? Let's see, even plugging in, right, x equals 0 here. So maybe more evidence as to why this isn't the right kind of connection, right? So plug in x equals 0, you're going to get sum from n equals 1 up to infinity of -1 to the n plus 1 times 2. And this series does not converge. Okay. So something went wrong here. Okay, and so the point of this example is that, well, okay, maybe we cannot differentiate term by term always and end up with the Fourier series. Okay. Well, okay, so what is true about all this stuff? Well, what is true is that generally, if you have a Fourier series that is continuous, right, meaning that it's continuous kind of on the interior of the domain, right, there are no jump discontinuities, and that the left and right endpoints, kind of in that fundamental domain, the value of the function agrees, right, then it'd be continuous, then you can differentiate the series term by term and end up with the Fourier series for the derivative of the function that you start with. Another way to phrase this is if f is piecewise smooth, so you can get a Fourier series, and f is continuous, so that on the interior of the domain, right, there are no jump discontinuities, then if the left and right endpoints of f agree, then you can differentiate your Fourier series term by term and get the Fourier series of the derivative of the function. Okay. And so actually written out, right, what does that look like? Well, if f of x is piecewise smooth, meaning you can take a Fourier series, and it's continuous, okay, you're going to get an equality between the function and its Fourier series. And so the kind of conclusion of the theorem is that then, well, what is the Fourier series of the derivative of the function? That's exactly what you get by differentiating each of the pieces term by term. Okay. Or stated another way, if this is a Fourier series for f, then this is the Fourier series for the derivative of f. Okay. And so we already saw that, right, here we can't differentiate term by term because this is not the Fourier series for this. Okay, and the reason is that, well, x, the Fourier series of x is not continuous, right? There are these jump discontinuities. Okay. Okay. And so it's actually helpful when talking about differentiation to split it up and focus specifically on the cases for when you have a cosine series and when you have a sine series separately. Okay, and so that's what we're going to do. Break up the cases, look at each part individually. Okay, so restating the theorem, kind of. So start with a continuous function on the interval 0 to L. So let's sketch something like that. So negative L to L, maybe some function like that. Okay. Then if you take its even extension, it's going to be something like that. And so its even extension in particular will be continuous on the entire interval because we won't have any jump discontinuities there. And if it's continuous over here, it'll be continuous over there. And moreover, the value of f at negative L is going to be equal to the value of f at L because we're taking an even extension, essentially. Okay. So in this case, the Fourier cosine series will be continuous. Okay. And so if we go back to the statement of the theorem, well, we have a continuous function, and its Fourier cosine series is continuous. So we can differentiate the cosine series term by term to get the Fourier sine series for the derivative. And so written out explicitly, right, if f is continuous, right, so so f of x continuous on the interval 0L, and this we can actually write as an equality, right, because we have convergence of the Fourier series to the function everywhere, right? So if we have our function be written like this, then the question is, what is the sine series of the function's derivative? Well, the sine series is what we get if we just differentiate these pieces term by term, right? So the sine coefficients for the derivative are going to be minus n pi over L times, right, the cosine coefficients. Okay. So kind of what does this look like in practice? Well, let's consider the Fourier cosine series of x, right? So this is going to look like the following. So here, we're defining x on the interval 0 to L. So we get that. If we want a Fourier cosine series, we take the even extension. So it's going to look like that. Okay. So really, the function that we're working with is absolute value of x, at least for this interval. And then we take the, when we compute this for a cosine series, right, we take this periodic extension. And so it's going to look something like this, etc. Okay. And so here in particular, the Fourier sine cosine series is continuous, so we can differentiate term by term. So this is the Fourier cosine series for x. Okay. Differentiating the left-hand side, derivative of x is 1. Differentiate the right-hand side, right? So the derivative of L over 2 is 0. Here, right, we're taking the derivative of 1 over n squared cosine of n pi over L x. And so this derivative, we're going to pick up what? So 1 over n squared is unchanged. N pi over L is going to come out. N pi over L times, so we're going to pick up a minus sign. Yep. Times sine of n pi over L x. Okay. So written down here, this piece right here is a derivative of that piece. And so let's see what cancellation we have. So this n is going to cancel with one of those powers of n. This pi is going to cancel with one of the powers of pi out there. This L is going to cancel with that L. And so what we end up with is this series is equal to this series, where we have 4 over pi, and then the sum over odd n of 1 over n sine of n pi over L x. And this is indeed the Fourier sine series of the function 1. And we can even sketch this. All right, so that's going to be 1, -1, L, negative L. Okay. So the sketch of the function 1 on this interval is that. Since we're taking an odd extension over here, it's going to look like that. And then we're going to take the periodic extension to get something like that. Right, so this is the sketch of this series. Okay, but in this case, this is the correct sine series for 1, and we're good to go. Okay, so the takeaway is that for Fourier cosine series, that's the nice case. You can just differentiate term by term, and that's the Fourier series for the derivative. Okay. So now what we're going to do is we're going to look at sine series, and what happens if you try to differentiate sine series term by term. Okay. So the issue is that in general, if you take a sine series, it won't be continuous. Okay. And so let's look at an example of that. So if we have, right, some function defined over here, maybe that's what our function looks like. And we take the odd extension, it's going to look like that. And then something like that, maybe. And so already you can see, because the value here is non-zero, there's going to be a jump discontinuity there. And so the Fourier sine series will not be continuous right here. Okay? And so we cannot differentiate the series term by term and end up with the correct cosine series for the derivative. So, right, you can say, well, if our function actually was 0 right there, maybe something like that, and then over here it matched up with the other pieces. Right. Well, over here, now the Fourier sine series, it would be continuous right here. Okay. And so that's half of our troubles kind of gone away. Right. But the other issue is, well, the value of the series over here is non-zero. And so because it's non-zero, right, the left and the right limits won't agree. So you could say, well, actually, if the function was 0 right here as well, and so 0 right here as well, okay, well, now the function is 0 there, continuous over here. So if we take its odd extension, it's going to be continuous over here. This value is going to match up with that value. And so then the Fourier sine series, it will be continuous. And so in this case, we can differentiate term by term. Right, but in general, the function that you might be interested won't be 0 at the endpoints, and so then the Fourier sine series won't be continuous. So you can't differentiate term by term. Okay, but there is something we can say about what the cosine series for the derivative should be in general. Right, and so the statement is the following. So if we have a function f of x, and we write it as a sine series, question is, what is the Fourier cosine series for the derivative of the function? And the claim is that, in general, doesn't matter what the function is, the Fourier cosine series for f prime of x will be this whole thing. Where, right, so this is going to be your constant term. And then this thing right here, this is going to be just the a sub n, the cosine coefficient. right? Yeah. And so one observation is, so maybe I'll just write it explicitly here. So note what happens when f of L is equal to f of 0, which is equal to 0. So if this happens, right? Well, over here, this is 0 and this is 0. So then this term goes away. And right, if we just differentiate this term by term, we wouldn't see a constant term. Likewise, if f of L and f of 0 are 0, then this is 0 and then this is 0. So then this whole thing goes away. And then this term is what we get just by differentiating term by term. And so this is a slight typo. So this capital B sub n, this should be little b sub n. But otherwise, yeah. Okay, but this formula holds in general. Okay, so when in doubt, this is the one to use. Okay, so let's see an example of how this plays out in practice. Okay, so we're going to revisit our example from before, where we're interested in the Fourier series of f of x equals x, the Fourier sine series of this, right? And so this was the example that we wrote out here. Right, so here what we saw, no, sorry, wrong example. Here, this is it. So here we saw that, right, if we try differentiating term by term, this is the cosine series that we end up with. And so then the question is, if we use the correct formula, do we get just 1 on this side, which is equal to 1, right? That's the derivative of f of x equals x. Right, so this is the Fourier sine series. So over here, that's the odd extension. And then kind of these pieces are the periodic extension. And then 0 right there, okay? So, right, this is the Fourier sine series for f of x equals x. And so in this case, right, the value of f at 0 is 0. The value of f at L is L. So what happens if we use a formula? Well, this is the formula copied from before. Okay. So what we're going to do is we're going to plug in f of L is equal to L right there and right there. And we're going to plug in f of 0 equals 0 right here and right here. Okay. So if we do that and then plug in the derivative of f, we're going to get 1. And what should the cosine series for 1 be? Well, following this formula, it should be 1 over L times L minus 0. And so, right, this is L. So then the 1 over L and L will cancel. So we're going to get 1 as a constant term, like that, which is already promising. And so what we want to hope is that, well, then this piece is going to go away. Because if it does, then, you know, we don't have any kind of non-zero cosine terms, which is what we'd expect. Okay, so plugging in here, and so this capital B sub n as before, this should read little b sub n. Okay, but what we're going to do is, right, so the question is, what is little b? Well, those are the sine coefficients for the original Fourier series. So these terms are exactly b sub n. So what we're going to do, plug this in to get this. Otherwise, we're going to plug in f of L is equal to L and f of 0 is equal to 0. Okay, so then this bit transforms into this. Okay, so you notice there's going to be quite a bit of cancellation. So let's see. So over here, n's are going to cancel, pi's are going to cancel, This L is going to cancel with that L. So we're going to be left with 2 times -1 to the n plus 1, which is what we have right here. Likewise, right, -1 to the n times L minus 0. That's just -1 to the n times L. And so this L is going to cancel with this L. And so we're going to be left with 2 times -1 to the n, which is exactly that. Okay. Okay, and so here, notice that, right? I mean, so another way of writing this, so if we factor out one of these -1s, we're going to get minus 2 times -1 to the n plus 2 times -1 to the n. Right, so this thing right here gives that, which is just 0. Okay. So these coefficients for the cosine terms, those are all just 0. And so in this series, all we're left with is this 1 at the front. Right? So, right, on the left-hand side, this was the derivative of the function we started with, right, which was f of x equals x. On the right-hand side, we end up with 1, which is, right, interpreted as a cosine series. Okay, so if we use the correct formula, then, you know, we get the right result. And so the thing is, right here, right, we're using this formula to kind of, right, take the coefficients from the Fourier sine series and adapt them into coefficients for the Fourier cosine series. The thing here is we need to be a little careful because there are discontinuities in the sine series, and so we can't just differentiate term by term. But if we incorporate, you might call these like correction terms. If you incorporate these correction terms, then you will end up with the correct result. So you can kind of differentiate term by term. You just need to add these correction pieces to get the correct result. But, okay, cool. Okay, so then the last thing I have to talk about is, well, how might we use this stuff to actually use these tools to actually solve PDEs? And so these fall under the name of what we'll call the method of eigenfunction expansion. Okay, and so what is this method? So method of eigenfunction expansion, the idea is, well, take eigenfunctions for your Laplacian, or take these eigenfunctions and then use these to construct a solution, a series solution to your PDE. And so, of course, in one dimension, what does this look like? Well, this looks like, say, d squared phi n dx squared is equal to lambda n phi n, right? So you're applying an operator to a function and getting back a multiple of that function. So that's your eigenfunction. And so once we have these eigenfunctions, we're going to construct a series solution, right, where kind of the spatial piece are coming from our eigenfunctions, and the time piece, these are just some coefficients depending on time. Okay. And so then, of course, right, depending on your PDE, right, or your PDE will tell you what you can say about these time functions. And then using that information, then you can figure out what the b sub n are and then solve your PDE. Okay, so let's look at what that looks like for some specific problems. So here we have the heat equation. Okay. Here we have boundary conditions. Right, so we're looking at the evolution of heat where we've constrained the temperature to be 0 at the 2 endpoints of this interval. And we have some initial condition, f of x times 0. Okay. And so the eigenfunctions that we get, right, these are eigenfunctions to this, right, d squared u dx squared is equal to lambda u. We're really just focusing on the spatial piece, but anyways. Or you can think of this as, right, through separation of variables, what's the spatial piece that we get? We get sines. Okay. And so what we're interested in doing is saying, well, right, we want a series expansion in terms of sines where we don't yet know what these the time pieces are. Okay? And so the question is, right, well, using the PDE, can we figure out what these b sub n are? Okay. Well, if we want to plug in this series representation to this PDE, we need to start taking derivatives. And so we take a time derivative, okay, assuming that we can distribute that time derivative across everything, which we'll justify here in a second. We're going to get the series, right? So looking back here, we're taking d dt of this thing. The only thing here that depends on time is this, and so that's what gets the derivative. Okay, and so here we're going to take an x derivative, and so in this case we'll end up with this. Now the observation here is, sure, we're differentiating a sine series, okay, but because the value of the series at 0, x equals 0, and x equals L, because the value is 0 there, right, for any fixed t, this sine series will be continuous, and so we can differentiate term by term. So when we take this ddx of this, we can distribute it, just take the derivatives of these things, right? Derivative of sine of n pi over Lx is n pi over Lx cosine n pi over Lx. And so then that gives us this expression, okay? Taking another derivative, distributing it to these things, you're going to get this piece right here, okay? Cool. So these are the two main pieces we need, right? And so what we're going to do is plug these pieces into the original PDE and just see what we can say about the resulting series. Okay, so right, to satisfy this PDE, we'll plug in the two series. So this thing right here, and so maybe I can write this. So this one, this is du dt. This one is d squared u dx squared. Okay. So plug in the series for each of these pieces, and notice here we've distributed the k to each of these terms. So now what we're going to do is move this series over to the other side and then collect like terms, right? So match up whenever we have a sine of n pi over Lx, sine of n pi over Lx there. Match those terms up. So there's a typo here. This should be a plus. Okay. But if you move this over there and collect like terms, you're going to end up with this thing right here. And so, okay, well, what is this telling us? Here, we have a sine series, right? Some coefficients times sine. And the claim is that this is the series, the sine series representation for the function 0. So the question is, well, if you have a sine series for the function that just gives you 0 everywhere, what should the coefficients for the series, the sine series be? Coefficient should be 0. If it helps, right, well, we can explicitly compute what these coefficients are, right? So these are going to be 2 over L integral from 0 to L of the function we care about, which in this case is 0, times sine of n pi over Lx dx. So we're integrating the function 0. Of course, this is going to give 0. Okay. So here we have a sine series for the function 0 that tells us that all of the coefficients should be 0. And so then the conclusion is that, well, since, yeah, so each of these terms is 0, so equivalently we get this thing right here. You can also write this as, right, b sub n prime is equal to minus k n pi over L squared b sub n, okay? And this is an ODE that you can solve directly, right? So the solutions for this ODE are going to be exactly exponentials of this form for some undetermined constant c. Okay. Okay. And so, sure. So what we have here is we've said, well, if we have a series solution of this form, right, what should these coefficients satisfy? And so in this case, we're saying, well, for the coefficients to work out, they need to be of this form, which matches what we computed using separation of variables and kind of going through that process. Yeah, okay. Right, so we have a solution of this form with these coefficients. And so one question is, well, can we actually write down what each of these coefficients C, or you might say C sub n, what they are? Well, here, right, if you plug in 0, you're going to get B sub n of 0 is equal to your constant times e to the minus k and pi over L squared times 0. This whole thing is 1. So you're just going to get C, right? So the constant showing up for each of these functions is, sure, the value of this function is 0, which shouldn't be a surprise. But what we can do is we can say, well, right, we also have other information about this problem, right? We have an initial condition. So if we plug in t is equal to 0, right, to our solution, sure, that's equal to f of x. But if you plug it into the series, you're going to get this expression right here. Okay. And so what you can do then is say, or notice that, well, these terms right here, these are exactly the Fourier sine coefficients for the function f. Right, or in other words, right, these b sub n of 0, these are exactly, so it's going to be 2 over L integral from 0 to L of f of x sine of n pi over L x dx. Okay. Great. But great, I mean, right, so what we've done is we said, well, if we want a series solution built off of eigenfunctions for this differential operator, so in this case, these sine pieces, what should these functions be? Well, we've seen that they need to be exponentials of this form, where these constants are the Fourier sine coefficients of our initial condition. Okay. Cool. And so, right, so this process matches up with what we got via separation of variables. And so you may ask, well, you know, why bother with this approach? The nice thing about this approach is it lets us solve a few more kinds of questions that separation of variables either would not have been able to, or if it could, it would have been too much work for what we'd be able to get out of it. But anyways, okay, cool. Right, so yeah, so one kind of fact that we used here was that, right, when we differentiated in time, sure, we weren't differentiating x, so we weren't differentiating a Fourier series, but we were able to distribute the derivative to each of the coefficients. Okay? And so the question is that justified? And the short answer is yes, it is. And so if you want a theorem or kind of statement for it, if you're working with the series of this form, so u of xt is equal to this sort of thing, then if you take the time derivative, your function, you can just distribute that time derivative to each piece, right? So then in particular, time derivative of u is going to be the time derivative of the constant, or the constant term, say constant in x, plus what you get by just differentiating these constants. Okay. And so the question is, well, why does that hold? Why might we expect that to hold? And so in general, if you have a nice enough function in general g of x and t, with two variables, the claim is that if you take the time derivative of the integral from negative L to L of g with respect to x, then you can move the time derivative inside and get the integral from negative L to L of the time derivative of g integrated with respect to x. Okay. Right, and so, I mean, you may recognize, I mean, so we use this property when we were setting up kind of some of these conservation laws and deriving the heat equation. So it's not necessarily something new, but right, it does appear explicitly here when we're trying to get these coefficients. But yeah, okay. So let me